Good morning, students. So, today's class we are going to study about the Butterworth and Chebyshev approximation techniques. Actually, these approximation techniques are mostly used for converting the analog filter into an analog filter itself. So, for that purpose only, we are going to use this Butterworth and Chebyshev approximation techniques. So, first one about the Butterworth approximation technique. So the magnitude, when we see the magnitude function of a Butterworth filter, in the case of nth order, so generally the formula it is given by modulus of HA of j omega whole square. This is equivalent to 1 by 1 plus omega by omega c whole power 2n, where n represents the order of the filter and omega c represents the cutoff frequency. So this is the general expression for the magnitude response of the Butterworth filter. And if you substitute the order of the value n, if you see that is for higher orders, we can get a better frequency response. And if you see the picture, this is the magnitude response characteristic of a Butterworth approximation filter. So in this, if you see this is an ideal low pass filter, this dotted line indicates the ideal low pass filter characteristics having the sharp cutoff frequency omega c. So the omega, it is in the angular frequency given in the x-axis, and the magnitude it is given in the y-axis. And if you see the first curve, this is an approximate version of a, practically when you implement, this is an approximate version of a frequency response of a low pass filter. So the first curve you represent for n equal to 2, we are getting the curve like this. But in this curves, if you see in the case of low pass filter, this is the pass band region and this is the stop band region. And this is the transition region, transition between pass band and stop band. In the case of ideal filter, you have sharp cutoff frequency exists. So in that case, this is the pass band region and this is the stop band region. Whereas in the case of approximate response, there is no sharp cutoff exists like an ideal filter. You can able to see at n equal to 2, here you are getting this curve. So in this, the low pass filter not only allows low frequency components to pass through, it allows some part of high frequency component also. That's why we are increasing the order of the filter. So now if we increase the order of the filter at n equal to 4, you can see that the curve little bit closer to the ideal filter to this one. So in that case also it allows some part of high pass high frequency component. And then for n equal to 8, you can able to see that this curve is little bit closer to this ideal filter. So that all in here also it allows some part of high frequency component. So like that when you increase the order of the filter, when the ideal response and approximate response nearly equal, when it both the curves meet, so in that case we can say that we have sharp cutoff exist. Okay, so for that purpose only we are going for Butterworth approximation techniques. This is the magnitude response of it. And here the filter practically when you implement you can able to filter characteristics like this. So when you increase the order of the filter and you can bring this ideal filter nearly equal to approximate response. So in that case we are going for this Butterworth low pass filter. So in the Butterworth approximation, so at omega equal to 0, the magnitude is equal to unity. And at the Butterworth filter, it is said to have the Butterworth filter, it is said to have maximally flat magnitude at omega equal to 0. So next, when you see the gain of the Butterworth filter in this, which is expressed in decibels, it is calculated by the formula g of omega equal to 10 log to the base 10 of modulus of h of j omega the whole square, which is expressed in decibels. So when you substitute omega equal to 0, the gain will be 0, equal to 0. And when omega is equivalent to omega c, so the gain is given by, so the maximum frequency for the Butterworth filter here it is given by modulus of HF j omega is 1 by 2. So when you substitute this g of omega c 10 log to the base 10 of 1 by 2 is minus 3.0103, which is approximately equivalent to minus 3 dB. So at omega equal to 0 the gain is 0, and at omega equal to omega c the gain is minus 3 dB. So this omega c we call it as a 3 dB cutoff frequency. So when we see the magnitude response, it is given by the formula modulus of h of a j omega whole square. It is approximately equal to 1 by omega c whole power 2n. For the case omega greater than omega c. So if you see the gain, or when the omega 2 is equivalent to 2 omega, suppose the assumption is the gain g of omega 2 which is expressed in decibels, and when you consider omega 2 equal to 2 into omega 1, so in that case omega 1 should be greater than 2 omega c. So you take the general expression here, in that we have to substitute omega 2 by omega c, and in the place of omega 2 we have to substitute 2 omega 1. So in that case when you simplify this, so it will be g of omega 1 equal to minus xn dB. So when you simplify this you will be getting minus xn dB. So here the gain in the stop band decreased by 6 dB per octave, whereas in the um, pass band it is increased by 3 dB as we have seen in the last expression. So here the pass band and stop band behaviors of magnitude response improve with decreasing in the transition band as well as the filter order n increases. And if you see, we have a concept called stop band edge frequency which is given as omega s, and pass band edge frequency which is given as omega p. So generally the pass band edge frequency omega p, it is determined by 1 by root of 1 plus epsilon square. So now we are equating, that is modulus of h of ha of j omega whole power whole squared. This is equivalent to 1 by 1 plus omega p by omega c whole power 2n. So which is equivalent to this passband magnitude response 1 by 1 plus epsilon square. And in the case of stop band edge frequency, it is 1 by 1 plus omega s by omega c whole power 2n. So which is equivalent to 1 by a square. So patch band edge frequency we are equating with 1 by 1 plus epsilon square, and stop band edge frequency we are equating it to 1 by a squared. So now based on the above equations, we can able to solve the equation for n value to calculate the order of the filter. So the final expression for the order of the filter is 1 by 2 log of square root of 10 power alpha s by 10 minus 1 divided by 10 power alpha p by 10 minus 1, which is divided by log of omega s by omega p. So when you simplify this, we will be getting the log of k sp1 and log of lambda sp1. So the Butterworth value of n, it can be used to solve for 3 dB cutoff frequency. To obtain the 3 dB cutoff frequency, the formula is, in the case of passband, it is omega c equal to omega p 10 power zero point 0.1 alpha p minus 1 whole power minus 1 by 2n. And when you want to calculate the for the stop band cutoff frequency, so omega c equal to omega s 10 power alpha zero point 0.1 into alpha s minus 1 the whole power minus 1 by 2n. So these are the two formulas in which the passband specification at omega p and stop band specification at omega s are calculated. So the next one is Chebyshev approximation technique. So in the Chebyshev approximation technique, so you can able to see it is not a, there is a ripples occurs in the passband as well as stop band. So that ripples is equiripple one. So in the Chebyshev filter, there are two types. One is Chebyshev type 1 and Chebyshev type 2. So in the type 1, there are equal ripple in pass band and stop band. But in type 2, so you have a monotonic in the pass band and equal ripple in the stop band. So that is the difference which exists between the type 1 and type 2. So when you see the magnitude characteristic of a Chebyshev filter, it is expressed as modulus of HA of j omega whole squared, which is equivalent to 1 by 1 plus epsilon squared Cn square of omega divided by omega p. So this is an expression for Chebyshev approximation. So where epsilon is, varies between 0 and 1. Cn is nothing but it is a Chebyshev polynomial of order n. So this is the magnitude response of an Chebyshev filter in which you can equal ripples occur in the pass band as well as stop band. You can able to see that. So next in the case of Chebyshev polynomial, how it is expressed is Cn of x is cos of n or cos x for modulus of x less than or equal to 1, and ch of n or x, modulus of x greater than or equal to 1. So this is an expression, and the relative polynomial is given by Cn plus 1 of x is 2x of Cn of x minus Cn minus 1 of x, where C naught of x is 1 and C1 of x is equal to x. So this is the formula used to calculate the Chebyshev polynomials. So now it has been seen that the squared magnitude response will equal ripple between x of 0 and x of 1, and it is monotonically decreases for all x greater than 1. Now this is the formula to calculate the order of the filter. So which is given by HA of j omega the whole squared equal to 1 by 1 plus epsilon square Cn square omega s by omega b. So in a short form we can express it at 10 power 0.1 alpha s. So we are equating with this one.